First problem says write 1 plus I to the 2013th power in the form x plus iy. In class, you've seen this more often written as a plus bi, same thing. So we're going to write, let's draw a picture first of this complex number and see what it looks like. So draw this on the complex plane, or the real complex plane. This number 1 plus I goes out 1 unit in the real direction, up 1 unit in the complex direction. So you can see that it makes a 45-degree angle, or pi over 4 radians. Now if we want to find the radius of this angle, or not the radius, think about it as the hypotenuse or the radius, basically just the length of this side here. That's just the Pythagorean theorem. So r is equal to the square root. This length here is 1, and this length here is also 1. This is 1 squared plus 1 squared, which is just the square root of 2. We can write 1 plus I as, in the cosine I sine form, as root 2 times cosine pi over 4 plus I sine pi over 4. Now the reason we do it this way is because when you raise a complex number to a power, in this form, there's a very simple way to do it. So if we want to do 1 plus I to the 2013 power, all that means is raising the right side to that same power. But you raise the r value to that power, root 2 to the 2013th. But you don't raise the trig part. You actually multiply the argument of the trig functions times the 2013. This becomes cosine of 2013 times pi over 4 plus I sine, same argument, 2013 times pi over 4. Let's try to figure out what 2013 times pi over 4 is in order to take the cosine and the sine of that angle. So let's think. Pi over 4 times, I want to break this up into an even number, so I'll say 2012 plus 1. I like that because 4 goes into 2012 503 times. So this is going to be pi times 503 plus pi over 4. Now, 503 pi is 251 and a half rotations. So I'm going to write this instead as 502 pi plus pi plus pi over 4. This is 251 rotations of pi. It doesn't really matter because every rotation you do on the unit circle, that you start here, and you do 251 rotations, you're just going to get back to the same spot. So we actually don't care about this. All we need to do is think about cosine of pi plus pi over 4. Well, this is, of course, 5 pi over 4. But really what we're evaluating now is the square root of 2, the 2013th power, times cosine of 5 pi over 4 plus I sine of 5 pi over 4. Now these are just unit circle values. Equal to, we'll clean this part up a bit at the end. Cosine of 5 pi over 4 is negative root 2 over 2, quadrant 3, and same thing with sine. Negative I square root of 2 over 2. Okay, we'll clean this up just a bit. This is negative, so we've got root 2 and root 2 on the numerator, so we'll say this is root 2 to the 2014th power. You're adding these exponents over 2 minus I, same thing here, root 2 to the 2014th power divided by 2. This is negative. Think about root 2 as 2 to the 1/2 power. I'm just going to write that out. 2 to the 1/2, 2014, all over 2, minus I, 2 to the 1/2, 2. And then you should be able to see that this simplifies. When you multiply, when you raise one exponent to another exponent, you can just multiply those two exponents together. So this becomes negative 2 to the 1007 power divided by 2 minus I 2 to the 1007 divided by 2. And finally, that's just equal to negative 2 to the 1006 minus I times 2 to the 1006. Okay, so we've got the right form. The real number here, the complex part here. And that's our answer. Okay, let's try the next one. Compute the indefinite integral x to the third times natural log of 3x dx. So typically when we're doing integration by parts, we're going to let u be the polynomial term and dv be the everything, whatever else. In this case, it's very difficult to integrate natural log of 3x. So we're going to actually let u be that part instead. U equals natural log of 3x. And then we'll let dv be the polynomial in this case. Now, take the derivative. Du equals 1 over 3x times 3 by the chain rule dx. Oh, I left off with dx here again. dv has to be some function and then including the dx so that you can integrate it. And then v is x to the 4th over 4. Don't need your plus c here. Integration by parts formula is uv minus the integral of v du. So this becomes x to the 4th over 4 times natural log of 3x minus the integral of v, which is x to the fourth over 4 du, which is, cancel these 3's, 1 over x dx. Simplify this a bit before we move on. X to the fourth over 4, natural log of 3x, minus, I'm going to pull the 1/4 out of the integral. And then I'm going to think x to the fourth divided by x is x to the third dx. Now I have to keep integrating. Integral of x cubed, that's an easy one, x to the fourth over 4 plus c. And then I can clean this up just a bit more. X to the fourth over 4, natural log of 3x minus 1 over 16 x to the fourth plus c. Okay, next one. Compute the indefinite integral. This one's a little complicated. This is going to be trigonometric substitution. So when we have something of this form, x squared minus a squared, our substitution is going to be x equals 3 secant theta, which of course means x squared equals 9 secant squared theta, and dx equals 3 secant theta tangent theta d theta. Now we have to rewrite this integral in terms of theta. So let's see. The top part becomes 9 secant squared theta. Take care of that. The dx becomes 3 secant theta tangent theta d theta. And the bottom becomes 9 secant squared theta minus 9 to the 5/2. Now don't simplify anything right away, just write it all out first and then we'll simplify as we go. So from the numerator I see 9 times 3, so I'm going to pull that out, that's 27. And then the secant squared, and the secant I'm going to write as secant cubed theta tangent theta d theta. On the bottom, I have two terms inside this expression. So I can factor out the 9, get 9 times secant squared theta minus 1. And all of that is still being raised to the 5/2. 27 integral. Let's see. This is 27 okay, so this becomes 9 to the 5/2 times this stuff. Secant squared of theta minus 1 to the 5/2. So what is 9 to the 5/2? Well, that's equal to 9 to the 1/2 fifth, which is equal to 3 to the 5th. So when I pull that 9 to the 5th out in front, I'm going to pull it out as 3 to the 5th instead. This becomes 3 to the 5th. Now, secant squared of theta minus 1, that's tangent squared, that's a trig identity. This becomes d theta, tangent theta, d theta, tangent squared theta, the 5/2. Okay. $27 is 3 to the third over 3 to the fifth integral. You don't have to write out all of these steps, but I just write them out to be a bit more clear. Okay. Tangent squared of theta to the 5/2. This is 2 exponent and a 1/2 exponent going to cancel, and you're just left with tangent to the fifth theta on bottom. We'll keep simplifying. 3 to the third divided by 3 to the fifth, that's just 1 over 3 to the second times the integral. Here you've got 1 tangent on top, 4 tangents on bottom. So we'll write this as a secant to the third of theta divided by tangent to the fourth, which is the same thing as multiplying by cotangent to the fourth theta, d theta. Remember that 1 over tangent is cotangent, the 1 over tangent to the fourth is cotangent to the fourth. All right, 1 over 3 squared, well that's just 9, so 1 over 9. And then this is a kind of an ugly integral, so I'm going to change everything into sines and cosines and see where that gets me. Secant to the third, that's 1 over cosine to the third. Of theta. Cotangent is cosine over sine, so this is cosine to the fourth of theta divided by sine to the fourth of theta. All right, 1 over 9. I've got 4 cosines up here, 1 cosine, 3 cosines here. I'm going to cancel all but 1. This is cosine of theta divided by sine to the fourth theta d theta. I'm going to do a little substitution here. This is a u sub integral, so I'm going to let u, remember I picked u to be something such that its derivative matches another part of the problem. So if I pick u to be sine of theta, the derivative of sine of theta is cosine theta, which we have on top, so that's great. U equals sine theta, du equals cosine theta, d theta. This simplifies my integral quite a bit. 1 over 9 times the integral of 1 over u to the fourth. Cosine theta d theta becomes just a du. I'll rewrite this for the purpose of integrating. Integral u to the negative 4 du. And then finally, this is 1 over 9 u to the negative third, adding 1, divided by negative 3. And we'll clean this up. This is negative 1 over 27 times, our u was sine theta, so we'll just write sine theta to the negative 3. But this is still a problem because we started this integral with x, so we need to end with x. Let's go back up to our substitution. x equals 3 secant theta. So x equals 3 secant theta. Well, this means, of course, x over 3 equals secant theta, which of course means 3 over x equals cosine theta, because secant is 1 over cosine, or just the reciprocal of cosine. So if secant theta is x over 3, then cosine theta is 3 over x. Now we're going to build a triangle using that information. Right triangle. We'll arbitrarily name this angle theta. So if cosine of theta is 3 over x, and then 3 over x is adjacent over hypotenuse, then that means this leg here is 3, and the hypotenuse is x. And that makes the last leg, by the Pythagorean theorem, the square root of, let's see, x squared minus 9. So finally, sine of theta is opposite over hypotenuse, square root of x squared minus 9 divided by x, the negative third power. And then don't forget your plus c. And that is our answer. Next problem. Determine if the improper integral converges or diverges. If it converges, find the value to which it converges. Okay. So we look at this integral, it looks a bit like a U substitution problem, so we'll just do that. Actually, we should be a little bit more formal. Natural log of 1 is 0. So this function doesn't exist at the endpoint 1. So we'll actually turn this into a limit problem just to be a little bit more formal. We'll say the limit as r, use any letter, goes to 1, and then times the integral from r to e of 1 over x times natural log of x for 1/3. Okay. Now we'll let u be the natural log of x. Again, we're picking this choice for u because the derivative is 1 over x, which we have in our problem. U equals 1 over x dx. Subbing that in. 1 over x dx is du, so this is just going to be du on top. On the bottom we'll have u to the 1/3. We'll clean that up for the purpose of integrating. U to the negative 1/3 du. Now we can integrate. This is u to the 1/3, 2/3, divided by 2/3, which is the same thing as multiplying by 3 over 2. Then we're going to back substitute whatever we substituted initially. Halves. See, our u was natural log of x. 3 2/3. We're going to evaluate that from r to e. So this is 3/2. So this limit, 3/2 times the natural log of e, 2/3, minus the natural log of r, 2/3. Okay, now we can take our limit, which is really just plugging in. Okay. The natural log of e is just 1. Any logarithm of 1 is 0. So 1 to the 2/3 is just 1. And our final answer is 3/2. So our integral does converge, and it converges to 3/2. Next problem. Find the volume of a solid region obtained by rotating this graph over the interval 0 to pi/4 about the x-axis. So we're rotating about this axis here. And let's get an idea for what this figure is going to look like. If you rotate this around, you'll have the same kind of shape on bottom. It's kind of like a sideways cone, so with a bit of a curve. Okay. The formula for the volume is pi times the integral r squared. Now, if we're adding up our little circles along the x-axis, we're adding up our disks along the x-axis, that means our integral is going to be a dx integral. So these bounds have to be bounds on x. And, well, we're starting our integral here at 0, ending at pi/4. That's what they gave us, so that's just 0 to pi/4. And then think about the radius of any of these given disks. Those are bounded by the cosine graph on top. So the radius is just cosine of 2x. So our volume is going to be equal to, let me write this out here, pi, the integral 0 to pi/4, and our radius function is just cosine 2x, but we have to square that by the formula, dx. So now they're just asking you to integrate this thing. But you have to use an identity. Cosine squared of anything is equal to 1/2 plus cosine of 2 times that same anything divided by 2. So in our case, cosine squared of 2x is equal to 1/2 plus cosine of not 2x but 4x divided by 2. So we can rewrite our integral with that identity instead. Integral 0 to pi/4, 1/2 plus cosine of 4x divided by 2 dx. Yeah, we can pull this 1/2 out just to be a little clean. Pi over 2 integral 0 to pi over 4. Pull the 1/2 out of both terms, you're left with 1 plus cosine 4x. Yeah. Now let's integrate. Don't need this anymore. This is x plus the antiderivative of cosine is sine. Inside stays the same. And then you divide by 4. If you don't know that shortcut yet, I think I have a video on that somewhere else. But you just integrate the function like you normally would and divide by the slope of the linear function on the inside. This is going to be evaluated from 0 to pi over 4. So let's do that now. Pi over 2, pi over 4, plus sine. Pi over 4 times 4 is just pi. Minus. And the lower bound, 0 plus sine of 0 divided by 4. Pi over 2 times pi over 4. Sine of pi is 0 minus 0. Sine of 0 is 0. Our final answer just becomes pi squared divided by our volume of our figure there. Problem. Determine whether the series converges or diverges. Justify your answer. Alright, so we'll compare this series using the limit comparison test. We'll compare it to another series that we understand something about. So let's compare this to, this will be our AN, and we'll let BN be 1 over n squared. And you'll see why I picked this in a minute, but this is a sequence, but if we take the series of Bn, that's a convergent P series because P being 2 is greater than 1, therefore that converges. So if we can show that the limit of this AN divided by our BN is a number between 0 and infinity, and that means our series both have to do the same thing. So if, and we already know that the series of Bn converges, so AN would have to also converge. So let's see what happens when we do this. Let's take the limit as n goes to infinity of just the sequences AN divided by Bn, which is equal to sine of 1 over n squared divided by 1 over n squared. So, as n goes to infinity, 1 over n squared goes to 0. The sine of 0 is 0, and the bottom goes to 0. So this is a 0 over 0 that's indeterminate form. You can apply L'Hopital's rule instead and say this is the same as taking the limit as n goes to infinity of the derivative of the top and the derivative of the bottom. Quotient of those. It's not a quotient rule, you just take the derivatives separately. This becomes cosine of, I'm going to write it as n to the negative 2, just so it's easier to differentiate. and then the derivative of the inside is negative 2 n to the negative 3. And then the derivative of the bottom is the same thing, negative 2 n to the negative 3. So I just rewrote 1 over n squared as n to the negative 2 for the purpose of taking the derivative. Okay, now we see that this stuff cancels, which is nice. So we're actually taking the limit as n goes to infinity of cosine of 1 over n squared. Again, we know 1 over n squared goes to 0. This is just really cosine of 0, which is from the unit circle, that's 1. So because this limit of the quotient went to 1, that means our series both have to behave in the same way. And the series n equals 1 to infinity of 1 over n squared converges by p-test. This means our series sine of 1 over n squared converges as well by the limit comparison test. So let's go through that logic again. We had a series that we didn't know how to work with, so we built another series that we knew converged by the p-test, and then we took the limit of the sequence of our series divided by the sequence of that new series, the quotient of those two sequences, and we got a finite number, a number between 0 and infinity. Because it was 1, that means our series have to both do the same thing, either both converge or both diverge. And in this particular case, our other series converged, so that means our sine of 1 over n series also has to converge by the limit comparison test. Okay, next problem. Find the interval of convergence for the power series x minus 7 to the n divided by n times 3 to the n. Okay, so when you're finding interval of convergence, 99% of the time you're just using the ratio test. So we'll apply that here. We need, for the series to converge, we need the limit as n goes to infinity of the absolute value of, let's see, okay, this is an. Actually, let me write that criteria out first. So we need the limit as n goes to infinity, the absolute value of an plus 1, a sub n plus 1 divided by an. We need this to be less than 1. So what we're going to do is figure out what a sub n plus 1 is. Well, that's just x minus 7 to the n plus 1. We're just writing an n plus 1 everywhere we see n, divided by n plus 1 times 3 to the n plus 1 power. That's the a sub n plus 1 here. And we're going to divide by the original sequence, but because it's a fraction, you're multiplying by the reciprocal. So this is just n times 3 to the n divided by x minus 7 to the n. And we need this to be less than 1. So we want to expand this a bit. The limit as n goes to infinity. This term here becomes x minus 7 to the n times x minus 7 to the first, using properties of exponent, times n times 3 to the n plus 1. This becomes 3 to the n times 3 to the first, same property of exponent, times x minus 7 to the n. Again, we need this to be less than 1. So we'll cancel some things, cancel this, 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 and this. The limit n goes to infinity. Whatever remains, n over n plus 1 times x minus 7. What is the limit as n goes to infinity of n over n plus 1? Well, that's just 1. So really what we're left with is x minus 7. We need this to be less than 1. Okay. So really, x minus 7 has to be less than 1 and greater than negative 1. So we get rid of the absolute value, which means x has to be less than 8 and greater than, I think there's a mistake here. Oh, I left off a 3 right here. It's 3 here. Let's fix that. Sorry about that. Okay. Really what we have now is n over 3 times n plus 1. So this limit actually goes to 1/3 times x minus 7. We need that to be less than 1. Okay. Now x minus 7 over 3 has to be less than 1 and greater than negative 1, which means x minus 7 has to be less than 3 and greater than negative 3, which means x has to be less than 10 and greater than 4. So right now our interval of convergence is 4 to 10, but we don't know if either side or either endpoint also converges or the series converges at those two endpoints. So we have to test each one. Okay, so let's go back into these original problems. Let's start by testing x equals 4. So when x equals 4, our series becomes 4 minus 7 n over n times 3 to the n. Which is equal to negative 3 n divided by n times 3 to the n equal to negative 3 over 3 is just negative 1, so this is really negative 1 to the n divided by n. So we recognize this as an alternating series. What we can do is take the absolute value of it, absolute value of the series, and we'll try to figure out what this is doing instead. Well, this is, of course, once you take the absolute value, the alternating piece disappears, and so we get this series instead, just 1 over n. Now this is the harmonic series, or just a p-series with p being 1. This series diverges. So that means that this series at the endpoint does not converge absolutely, but it could still converge conditionally. So we'll test that now. What that means is looking at this sequence here, 1 over n, and testing a few things. This is the Leibniz criteria. Okay, so 3 things to check. Does it have positive terms? Obviously that's true, 1 over n. For n being from 1 to infinity, those are only positive numbers, so that's the easy one to check. The limit as n goes to infinity of 1 over n has to be 0, which is again obviously true. As n gets very, very large, this sequence goes to 0. And then finally we want to make sure it's decreasing. So we'll write f of x equals 1 over x, just the corresponding function, and then we'll take the derivative of this. F prime of x equals negative 1 over x squared. And clearly this is less than 0 for all values between 1 to infinity, which means our function is decreasing. So our interval does include x equals 4. We'll put an open bracket, or a closed bracket there. Now we have to test the endpoint at 10. So we'll write that one out too. Equal 1 to infinity. 10 minus 7 to the n divided by n times 3 to the n. Equal to n equals 1 to infinity. This is 3 to n divided by n times 3 to the n. It simplifies. It should be the series 1 over n. Again, that's a harmonic series, or this p-series where p equals 1, and so this series diverges. So it diverges at the right endpoint. Our interval of convergence then is just 4 to 10. If they ask you the radius of convergence, you would just take the half of this interval, half of the length of the interval. Okay, next problem. This will be the last problem. Find the Taylor series centered at c equals 1 for f of x equals e to the 3x. Your answer should have this form. Okay. So f of x is already given. Remember the Taylor series formula. F. Now this notation here means the derivative, not a power. It's like f to the first is, or f with a 1 here would be the first derivative, 2 here would be the second derivative, and so on, of c times x minus c all over n factorial. This is to the n here. So this is for a Taylor series centered at c, for any c value. Our particular c value is 1. our formula is going to be the nth derivative of evaluated at 1 times x minus 1 n divided by n factorial. Let's see if we can get a formula for this. For n equals 0, f, we'll write it like this, we don't have to, but f0. This basically just means the 0th derivative or no derivative, which is just the original function. So this is going to be the original function. And then f, that means f of 1 is equal to e to the third. N equals 1. Now we're actually working with the derivative. The derivative by the chain rule is 3 e to the 3x, which means f prime of 1 is equal to 3 e to the third. N equals 2. Second derivative is 3 times 3, because you're going to do another chain rule here. So this is 3 squared e to the 3x, which means the derivative at 1 is equal to 3 squared e to the third. You should start seeing the pattern here, but we'll do one more. N equals 3. Third derivative is 3 to the third e to the 3x, which means the second derivative here. The third derivative evaluated at 1 is 3 to the third e to the third. And finally, for n equals n, f, the nth derivative, is equal to 3 to the n e to the 3x, which means the nth derivative evaluated at 1 is equal to 3 to the n times e to the third. So now we can just plug in. This term here corresponds to this. We'll say f of x is 3 to the n times e to the third. This part, there's not really much to rewrite, so x minus 1 to the n divided by just n factorial on bottom. And that is our Taylor series, centered at c equals 1.